Hi class, let's do an exam 1 recap. So we'll go through most of the problems and discuss solutions or perhaps just partial solutions to these problems. And hopefully after seeing them, this is what happens in a mathematics course. We throw new problems at you and you're expected to solve them, on the spot, which is very tricky. But we learn. So let's recap. Let's make sure that what the problems that we've seen now, we fully understand so that in the future, perhaps on the final exam, if we encounter these concepts or similar problems, we can recreate them because we have a better understanding of these topics. So problem number 1, we were given a function from a set x to y, and we wanted to prove an equality of sets here. Okay, so what we wanted to show was an equality of sets. So that forces us to show two things. And the first thing is we needed to show containment one direction. So we needed to show that the inverse image of this set y naught minus y1 is a subset of the inverse image of y naught minus the inverse image of y1. And this was where y naught and y1 were subsets of the codomain y. And then we needed to show our reverse inclusion. So we needed to argue that the inverse image of y naught minus the inverse image of y1 is a subset of the inverse image of y naught minus y1. Here. Okay, so to show the first, we can take a generic element let's call it x in the inverse image of y naught minus y1. Now remember, in the back of our head, what we are remembering is that the inverse image of a set consists of all x in x such that f of x is in x. And this is for a function going from x to y, so s is a subset of y, so the inverse image is a subset of x. So we're going to use this definition here. So by definition, this means that that x is in x and f of x is in y naught minus y1. Right? If we're an element in here, then we're in x, and if we move it forward, f of x is in this set. Now, what does it mean? Now we're going to focus on this statement. What does it mean for f of x to be in the difference? So hence, f of x is in y naught, and f of x is not in y1, right? We're in the difference. We're in here, but we're deleting being a part of here. Now, since f of x is in y naught, we know x is in the inverse image of y naught. Using this definition in reverse. If we're in here, then pushing it back, we're in here, right? So we're saying we're in here, so moving it back, x must be in this inverse image set. Similarly, since f of x is not in y1, x is not in the pre-image of y1. Hence, x is in f inverse of y naught, and x is in the inverse, and x is not in the inverse image of y1, showing x is in f inverse of y naught minus f inverse of y1. So we've taken a generic element here and using definitions and set arguments, we've argued that that element is in there, showing that we have this being a subset of this. So try the reverse direction here. So try this one. Okay, very similar argument, just going the other way. Okay, so number 2, we had a collection of topologies on a set X, and we wanted to show that the intersection of those is a topology. So we must show this defined tau for alpha in some indexing set of tau alpha is a topology. So we need to show that this satisfies the 3 conditions. Okay, now condition 1, we need to argue that x and the empty set are part of tau. But notice that each tau alpha is a topology, so x and the empty set are part of tau alpha for every alpha, so therefore, by definition, if it's in every single one of these, it has to be in the intersection. So that's a very easy single one-line statement or maybe 2-line statement saying that it's in here for each alpha, therefore it must be in here because it's in the intersection. A little more tricky, but not too much. Let's argue condition 2. So if we take a generic collection we'll call them AJ for some indexing set J of non-empty members of tau, then we need to argue, so in the back of our head, we need to argue that the union of these members is a member of tau. Here. Okay, so let's use the fact that each tau alpha is a topology. So the union must be in each of those, and then we can argue that since it's in each of those, it must be in the intersection. And so therefore it's in tau. Okay, now, so let's write that. Now since AJ is in tau alpha, is in tau, each AJ must be in tau alpha, because tau is defined to be the intersection. For all alpha in this indexing set. But tau alpha is a topology on X. So the union of these AJs is an element of tau alpha for each alpha. Hence, the union of AJ is an element of tau, because tau is the intersection. Okay, very similar argument for number 3. If we take two sets and look at their intersection, we need to argue that the intersection is a part of tau. So try that. So formally write condition 1 and condition 3, and include this as condition 2, and then putting it all together, we have proven the second question on the exam. Okay, so number 3 we've seen before. It was part of our homework. It was also part of the exam 1 review. So notice that we want to show this collection B is a basis for a topology. So remember, if we're just showing a collection is a basis for a topology, we need to show two things. And the first is that the entire space, so we're talking about the product space, can be written as a union of these members, and this is where we have B1 a part of a basis B1 for X, and B2's part of our basis B2 for Y here. So we need to argue this, but we also need to argue that if we take two elements in our collection B, then the intersection is a union of members of our collection here, right? And again, how we argue this, a lot of set theory pushing the set theory through, but since these two are elements of our set, then B is some B1 cross B2. B prime can be written as some B1 prime cross B2 prime. And then using some set theory, we can argue that this intersection equals something that looks like this. So look back at the exam 1 review and your homework for that problem. Okay, number 4 was slightly different. We had the subspace topology, and we wanted to argue that this collection is a basis for the subspace topology, for a specific topology. So we don't argue this, we need to argue something slightly different. And let's recall that the subspace topology is defined as follows, right? It's all the open sets in X intersected with Y, and that creates our subspace topology here. So for the question, we need to show that if we take an open set, we'll call it A, which is a subset of Y, with an element in A, then there is a basis element B such that A is in B is the subset of A. Here, okay, so let's do this. So our proof, so let A be a subset of Y, be open in Y, and let A be an element of A. Since A is open, A can be written as some O intersect Y, where O is open in X. Right? Okay, so now A is in O, and B is a basis for X. Hence, we can find a B in this set B with A in B, subset of O. Hence, A is in B intersect Y, which is a subset of O intersect Y. Here, so I've argued that I can fit one of these inside, still containing this point in my open set. Here. Okay, moving on. Here. Number 5, we have that f is a function from a topological space to another topological space, and we're given that f is continuous, and then we want to argue that if we take a closed subset of the codomain space, when we bring it back, looking at the inverse image, it's still closed. Here. So number 5, what we want to do is we want to take a generic closed subset of Y. Let's call it S. And argue the pre-image, the inverse image, which is in the space x tau, is closed. Okay, so since S is closed in Y, we know the complement is open in one. But F is continuous. So that the inverse image is open in X here. And now my hint was to use number 1, so notice that the inverse image by number 1 is the inverse image of Y minus the inverse image of X. But this is just X minus the inverse image of S, which is open, showing F inverse of S is closed. Right? Because we wanted to argue this is a subset of X. We wanted to argue that that's closed. Well, look, the complement is open. Because the complement equals this, and we already said this was open because F was continuous. Okay, and then finally, number 6, dealing with R being, the space R being Hausdorff. We saw that in our homework. The idea is that we can create so number 6, if we have R, I'm not going to prove it formally, but I'm going to argue it visually. So if we take 2 points in R, A and B, then we want to create open sets around A and B that are disjoint. Well, we can create them to be small enough so that they don't overlap, right? And remember, the open sets are open intervals, so notice there's no overlap. So this is an argument. So you have, the key here is finding a correct radius of these intervals centered at A and B so that they don't touch. Here. Okay. And then number 7 was a proof dealing with connected spaces here. So if we have 2 sets, A and B, that are connected, and they have a point in common, then their union must be connected. So give that a try. I'm not going to give you the answer to that one quite yet. If you're stuck, please email me and we can discuss it via Microsoft Teams, or we could just communicate back and forth via email.